Okay, let's get started with the afternoon session. And then we have many more interesting talks for this afternoon. And it starts with Dave Bonan. Okay.
Yeah, so I'm Dave Bonan. I'm a fifth-year PhD student at Caltech. Work I've been doing with one of my advisors, Tapio Schneider, and then Jung Chu here at NCAR and Thorsten Morrison at Stockholm University. I think this talk might be a little too simple, but we'll see how it goes. It's just basically asking the question of what does precipitation look like in extremely warm climates, but simulated with comprehensive GCMs. And so the main question we're going after is what does precipitation look like in extremely warm climates? And I think that a lot of people are probably aware of this kind of conceptually convenient way of thinking about precipitation changes through this hydrologic sensitivity. And I just called it eta here, but what it says is it's the ratio of precipitation change to temperature change normalized by the precipitation climatology. And if you kind of estimate this from climate models under like an abrupt 4 times CO2, you find that models say that this eta parameter or globally is just 1 to 3% per Kelvin. And what that means is that for every degree of global warming, you actually only increase precipitation by 1 or 2%, which is quite small. But we know that this kind of eta parameter scales with regional hydrologic changes, regional precipitation extremes. So there's kind of a lot of value in trying to constrain the global hydrologic sensitivity. And so I asked the question of what does precipitation look like in extremely warm climates? And I think we can just do a simple kind of scaling analysis from this and say that, well, maybe our best estimates of early Eocene temperature, surface temperature changes were 12 to 15 degrees warmer from today. So with a 1 to 2% per Kelvin from climate models, that would say a 12 to 30% increase in global mean precipitation. And you like solved it. But I'm going to say no if you didn't solve it. And the reason for this is actually there's a really nice paper back from Paul Gorman and Tapio Schneider in 2008, where they took an idealized GCM and kind of varied the optical thickness of the atmosphere. And they looked at how does that scale with precipitation. And what you see is that for global mean precipitation on the y-axis here and global mean surface temperature on the x-axis, precipitation scales pretty linearly for these kind of colder to today's climate regimes. But as you get towards these higher climate regimes, it begins to saturate. And actually, for every increase in global mean temperature, there's no increase in global mean precipitation. But there's a lot of kind of caveats to this. So they use this kind of idealized gray radiation model. It was an aquaplanet, so there's no land. The gray radiation scheme kind of assumes that radiative fluxes are just a function of temperature alone. And then kind of most importantly, there's no clouds or sea ice. So there's just a lot of variables here that didn't occur. But it still was kind of a good paper to kind of say, well, what would precipitation look like in extremely warm climates? And the way they began to understand this was globally, precipitation must be equal to evaporation on annual timescales. So they just looked at the surface energy budget. And what I've written down here is just the surface energy budget where there's 0 is balanced by short wave, long wave, evaporation, sensible, and then any ground heat flux or storage by the ocean. And what you can do is just rearrange this to say that, well, globally precipitation equals evaporation, and it's a function of these short wave, long wave, sensible, and ocean heat storage terms. And so what they showed was that as you kind of increase global mean temperature, there is no storage in this model because it's an aquaplanet. The sensible and the latent, or the sensible and the long wave fluxes end up going towards 0, and that's just because the atmosphere becomes so optically thick, it radiates the same energy down as much as it radiates up. And so really what you see is that precipitation is just balanced by shortwave radiation here at the surface. And so this kind of solid line here on the plot going across the x-axis is actually just the shortwave implied radiative flux. And you can see that at this kind of warmer temperatures, evaporation or precipitation equals that flux. And so this kind of gives us our theoretical understanding of what precipitation might look like under extremely warm climates. And actually it starts to say that if you didn't trust this kind of linear hydrologic sensitivity, that there'd be lower estimates of precipitation in extremely warm climates. But again, I said there were these big caveats. So what does this look like in more comprehensive models? And so the big question we have here is, how does precipitation, or what does precipitation look like in extremely warm climates with these comprehensive GCMs? And so for this, I'm going to actually use the simulations that Zhang and Chris Polson ran in 2020. And these are a set of simulations of slab oceans, but coupled to CAM4, CAM5, CAM6, so the community atmospheric model, the various versions of that. And it was forced with a 1 times CO2 all the way up to, actually, Zhang Chu just ran these 256 times CO2, and which is quite wild, but probably very unrealistic as well. But basically, there's kind of a range of climates we're spanning here. And I just want to point out how wild and unrealistic this is. So 256 times CO2 is what, 71,680 parts per million. So it's like just completely opposite what we think is going on, but at least it allows us to kind of probe this extreme climate scenario. Okay, so, and then what I should note is that some of the simulations crash under high CO2 values, and this has to do, I think, with tropical convection or some kind of, you just said a nameless table or something in the model. So there's a various set of mismatch of simulations, but I'm going to start off with the CAM6 one, and go to CAM5, CAM4. And so what I plotted here is surface temperature on the y-axis as a function of the CO2 forcing for 1, 2, 4, and 8 times CO2. And on the middle panel is precipitation as a function of that CO2 forcing. And then the right panel is precipitation as a function of temperature. So you can see that kind of linear relationship where there's the hydrologic sensitivity. And what you see is that there's no kind of saturation of this precipitation at extremely warm climates that we saw in this idealized GCM. It's all very linear. If you put on CAM5, the same story exists. So despite there being maybe a somewhat higher climate sensitivity at these higher CO2 values in this model, there's still a pretty linear regime between precipitation and surface temperature here. And then what's neat is with CAM4, we were able to run these simulations all the way up to 256 times CO2. And that's where you begin to see these kind of really interesting behaviors. So there's a pretty linear regime from today's climate all the way up to about 320 Kelvin. And then that's when you begin to see this kind of saturation of precipitation. And actually what you see is a decrease in precipitation despite there being an increase in temperature, which is not really that intuitive. And so this was like a hypothesis we had, and I'll kind of work you through what we mean by that. But I should also note that the radiation scheme at these high CO2 values is probably very inaccurate as well. So there's probably a lot of caveats to this, but it's really just allowing us to kind of start to explore these higher CO2 or warm climates. Okay, so yeah, what you see is precipitation increases or decreases as you increase temperature. So let's go back to that surface energy budget and look at the kind of components that add up to this. So again, I'm just going to say that global precipitation is equal to global evaporation, and then it's all based on the surface energy budget of short wave, long wave, sensible, and then any ocean heat storage. And what I'm plotting here on the top plot is the long wave flux as a function of global mean surface temperature. So again, what you see is that it does begin to decrease, meaning the atmosphere is becoming more thick, it's radiating energy to space, it's kind of matching the temperature at the surface. And I plotted here the total and the clear sky just to show what the cloud component would look like. So you see cloud component kind of goes back down towards 0. The short wave component is actually stuck around this kind of maximum of about 5.9 millimeters per day. But if you were just to look at the clear sky, there's actually this decrease. And what's going on there is basically your atmosphere is holding more water vapor. So it's absorbing more shortwave radiation that can't hit the surface. So there's actually a decrease in the surface net radiation. Sensible doesn't really decrease too much, and then ocean heat uptake was 0 because these are slab ocean simulations. But again, so I'm going to plot the CAM5, generally the same story. Maybe you see slightly different kind of magnitudes of these values, but you see a general decrease of the sensible heat, decrease of long wave, and then clear sky short wave kind of decreases as well. But what's really neat is when you put on the CAM4 simulation, where you saw this kind of decrease in precipitation as a function of temperature, you see that once you get to these higher regimes, the long wave flux is essentially 0. And that's just because, again, the atmosphere is optically thick. It's just radiating the SEM energy down as it's being emitted from the surface. The cloud component 0, and so is the sensible heat. And so with no ocean heat uptake, essentially your precipitation is just balanced by whatever's going on in your shortwave radiation. And so you see that generally this clear sky decreases quite a lot. And so the cloud component kind of saturates, and what that implies is that there's actually a generally decrease in precipitation, which is kind of what our hypothesis was, with that when the atmosphere has a lot of water vapor, it absorbs more of that shortwave radiation, it just doesn't reach the surface, so you can decrease precipitation. Okay, so this is cool. It's all just one model, or it's 3 different atmospheric models, but all one kind of modeling framework. So the next kind of question we had was, if you look at other models, what can we glean from this? And it's kind of hard to do this because not a lot of modeling centers run 1 times, 2 times, all the way up to say 64 times CO2. But there's this really nice set of simulations that Ria Rubenstein and Jonah Block-Johnson compiled back in 2019 as part of Long Run MIP. It's basically a set of simulations where these are fully coupled models run out to equilibrium. So 5,000 years, 4,000 years, 2,000 years, or quasi-equilibrium. And so what I did is I took the 1 times, 2 times, 4 times, 8, and 16, and I just averaged over the last 30 years of this millennial simulation, and just to say that's quasi-equilibrium. And again, now what you're looking at is 6 different models as a function of global mean surface temperature, CO2 forcing, and then precipitation, CO2 forcing, and then that kind of hydrologic sensitivity. So precipitation as a function of temperature. And generally what you see is that models kind of for today's climate up until about 295 Kelvin are generally in the same realm of a linear increase. There's no saturation. But once you get towards these higher values, say beyond 300 Kelvin, that's when you see models get diverge. So the MPI model here in brown is saying that there's actually starts to be a saturation of precipitation. had CM3 model says that there should be saturation earlier than that. But then if you look at this famous model or even earlier versions of the CSM model like CCSM3, there's just a linear increase. So models are just basically all over the place at these high CO2 values or warm climates. And so I think it's really important to, I'm going to show you the kind of mechanisms of why this happens, but to maybe have more simulations that probe these kind of 32 times CO2 climates among models. So yeah, again, if we take this kind of surface energy budget perspective on global precipitation, generally what you see is that models generally agree what the long wave flux should be. I can break this down into clear sky and cloudy just because the model simulations don't provide that, that data. So again, this is the long wave flux, short wave flux, sensible, and then ocean heat uptake. What you tend to see is they all generally agree on the like rate of change in the long wave flux. But really it's this kind of short wave flux that's determining whether it decreases or whether it's constant. And notably, there's no kind of change in the sensible heat flux, which is quite interesting. And so I think, you know, if I'm comparing this to like Tapio and Paul O'Gorman's work back in 2008 versus these simulations from CSM or from CAM 4, 5, and 6, these are now fully coupled dynamical oceans. There's presumably a lot of ocean circulation shifts that have changed what the sensible heat fluxes might be. And I think what this is all telling us is just we need more simulations for 2 times, 4 times, 8 times, up to 32, 64 times CO2, but in fully coupled models, just because they're all over the place at these really warm climates. So I have some quick summary and then I'll go into some other work. But generally what we found is that global precipitation increases linearly with surface temperature for about 10 degrees relative to today's climate. In extremely warm climates, it can saturate and begin to decrease. And that's what we saw in the CAM4 simulations. And this is because the atmosphere becomes optically thick, the net radiative flux is kind of radiating energy down at the same rate it's being radiated back from the surface. That means the sensible heat flux is 0, and essentially precipitation is balanced by the net shortwave flux. And then as the atmosphere warms, it absorbs that shortwave radiation because of more water vapor, so it can't reach the surface. And then I just threw in here, clouds are extremely weird at high CO2 values, and that can also change the story greatly. So we just need more simulations that examine, I think, these extremely warm climates in a broader suite of GCMs. And so this was all the global story, and I just want to end, I'm kind of doing a more regional perspective as well. So you can make an equation here that says precipitation is balanced by the net shortwave radiation at the top of the atmosphere and the surface. Same with the long wave, that dry static energy flux, and then any sensible heat flux changes. And this allows you to look at precipitation from a regional energetic perspective as well. And so if you look at these simulations from CAM 4, 5, and 6, on the top panel is the zonal mean surface temperature, and on the bottom panel is the zonal mean precipitation. And I've just ordered these based on those kind of 1 times, 2 times, all the way up to 256 times CO2. And I think what's really neat here is you know, at these extremely warm climates, there's very little temperature gradient meridionally. And that would imply that there's very little dry static energy fluxes towards the polar regions. And so your precipitation is probably going to be balanced by these radiation terms. And I just think that there's a lot of kind of interesting work we can do from gleaning these simulations and looking at kind of hydrologic cycles. So this is what I'm kind of doing as a follow-up or continuing with this study, but I didn't have time to do it for this workshop. So I'm happy taking questions. I'm currently trying to write up a manuscript with some of these results. So thanks.
Okay, very nice talk. Do we have questions?
Yeah, the first one is so 1 to 2% per Kelvin would be exponential, right? Not linear. If you look at P versus T, because it's not.
Yeah, but you have
Is
to go
it
to
just
like,
small that you don't see the nonlinearity there, or is there something offsetting what you expect from theory?
well, I think it's just that 1 to 2% is like these pre-industrial
Sorry.
the pre-industrial control versus a 4 times CO2. And so then you just assume it's this linear thing. But yeah, no, not many people look at these kind of higher CO2 or like extending these simulations to then look at like how that scaling changes.
Mm-hmm.
But what you end up seeing is that like from 1 to 2 times CO2, it's about 2% per Kelvin. From 2 to 4 times CO2, it goes to 1.5. And then from 4 to 8 times CO2, it goes to like 1. So it kind of starts to saturate. So the point was there was no like kind of theoretical understanding, I guess, of why there's that saturation.
Right. The saturation is not predicted at all. But
Yeah.
1 to 2%.
Yeah.
And second quick question, have you looked at like cloud resolving model simulations? Because your explanation seems like those simple regional, or I mean limited domain models could capture it too.
No, I haven't. I think there are people that have looked at, I think Tim Merlis at Princeton has looked at like precipitation scaling, and Tim Cronin at MIT precipitation scaling as a function of these extreme climates, but in like a 1D model. But I don't know about like a global cloud resolving or any of that, but it would be really cool.
Mhm.
Yeah.
Thanks.
Yeah.
One other question, since the role of the shortwave fluxes was so important, is it only the shortwave absorption in the atmosphere that matters, or is there any role for like sea ice, other things that affect the shortwave radiation balance?
Yeah, I think, well, so I think that once you get rid of, so if you have your sea ice, if you got rid of it, you should be absorbing more surface radiation or more solar radiation to the surface. So that would generally imply more increased precipitation. And so that was one. And then what we did here was we actually looked at like the full, at least for CSN, you can look at the full 3D budget and you see that there's generally just more absorption of sort of it like in the upper atmosphere. That was where we kind of made that conclusion, but
That makes sense.
yeah.
Ryan, you have a question?
Yeah, David, thanks for this very interesting talk. Just to follow up on the previous question, so I was wondering, is applying this to paleoclimate, so paleoclimate is not only just forced by CO2, right? So we have like land surface feedbacks, which turns out to be very important for setting up not only global mean temperature, but like the terrestrial hydrological cycle. So I was wondering, what might happen, or have you guys thought about maybe using some of the like simple land models to see what happened if you, let's see, changing surface albedo, for example, and changing, let's see, the soil water holding capacity, something like that?
Yeah, totally. I have not done that, but I've definitely thought about it. I think like one thing I also learned in this exercise was going from the gray radiation aquaplanet, I added land, and then even land changed the story, just having, instead of 100% ocean, 70% ocean. And so then it got me thinking that, yeah, you could probably change the boundary conditions of land in the paleo context, and that would change this whole story as well. But I haven't gotten to that. This was like the first stab at just trying to say, we think precipitation shouldn't increase always with global mean temperature. But yeah, it'd be really cool to do that.
Great, thank you.
Paul, go ahead.
Hey, great talk. So you said these runs are slab oceans, so I know Jung has some polycoupled stuff. Have you like tried plotting them against these simulations?
I have not. I actually did not know there were these fully coupled simulations, so that would be cool to look at. Yeah. I wouldn't expect it to change too much if the fully coupled were run out to equilibrium, but I think it would be cool to at least see what that role that sensible heat flux plays, if it actually decreases or if it just stays constant. Yeah. I'll make note of that.
Since we have time, can I ask another quick question about the radiation? You mentioned that the radiation may not be accurate enough. So do you have any plan for using more accurate radiation, or do you have speculation whether this will change the story in any way?
Yeah, I think you are aware of, you sent me there's these simulations that involve a more accurate radiation scheme that are higher CO2 values. So I at least would like to check that, yeah, validate it against, say, what this plot would look like at those values. But yeah, I think I'll do that. I just haven't had the time.
Is it feasible to do some line by line calculation? Or is it too expensive?
I think it could be, but I'm also trying to write my thesis. So I need to get graduate. No, I think that would be cool.
Thanks.
Yeah. All right. Thank you.
Exactly.
Okay, our next talk is a remote talk from Andrea Salazar. Andrea, are you online?
Yeah, hold on. Let me see if I can share my screen. Can everyone see that okay? Okay, great. So I'm Andrea. I'm a graduate student at Harvard University working with Ellie Zipperman, and we've been collaborating with Zhang and Brian here at NCAR to investigate the role of subtropical stratocumulus breakup in a warm climate using cloud blocking in CESM2. So we've heard a lot about the Eocene today, but I'll just give you a quick recap to get us all on the same page. This was a period about 50 million years ago that was characterized by higher CO2 values, maybe between 3 and 8 times pre-industrial, though there are pretty big error bars on that. And some notable features about this time in Earth's history is that the average surface temperature was much higher, maybe about 30 degrees Celsius. And this period was also marked by a reduction in the equator to pole temperature difference, maybe 30% reduction versus today. But kind of like a big puzzle of this time is that we have fossil evidence of frost-intolerant species at really high latitudes. So things like crocodiles and palm fronds, things that we know could not survive even a day below freezing. And though modern GCMs have had some success in recreating kind of like the global features of this time period, it's been very difficult to explain how to have no minimum temperatures below freezing in the continental interiors. And so a very popular theory that's been proposed many times is that maybe there are just cloud feedbacks that are very important for this question that are not being well represented in GCMs. And so the focus of this project and kind of the remainder of my thesis is trying to understand if cloud feedbacks missing from the current GCMs can provide additional warming mechanisms to help us explain these above freezing temperatures in the continental interiors during the Eocene. So for this talk, I'm going to focus specifically on stratocumulus clouds. These are low latitude, low altitude clouds that cover about 6.5% of Earth's surface. And because of their low altitude, they have a really strong albedo effect. They can have shortwave cloud forcing of up to 100 watts per meter squared in these regions where they occur. And recent work using cloud resolving models has shown that as you increase CO2, you can lead to a disruption in the convection of these clouds that couples the clouds to their moisture source of the ocean. And if you have a complete breakup of these clouds, a very quick back of the envelope calculation suggests that maybe you can get up to 8 Kelvin of global warming just from a breakup of these stratocumulus clouds. But it's not obvious how this warming would be distributed globally and how relevant it actually is for the Eocene. So the motivating questions for this study is how much global warming would an abrupt breakup of stratocumulus clouds actually induce? So if you had a simulation and then you branch from that simulation a model run that has no stratocumulus clouds at all, so you would increase surface temperature, versus a simulation that had these very strong stratocumulus clouds, what is the global average temperature difference between these two states? And we're also interested in how much warming is actually transported to the higher latitudes, right? Because these are subtropical clouds. It's not obvious how much warming we would actually see in the high latitudes. And finally, we're interested in whether or not stratocumulus cloud breakup can actually help mitigate these below freezing days in the continental interior. So this is an example of like a histogram of the minimum daily temperature in a region. And we want to see that we kind of remove this below freezing tail from the distribution with a breakup of these clouds. So the way that we're going to do this is by using cloud locking in CESM2. So the way that cloud locking typically works in CAM6 is you perform a reference run where you allow the model to make the clouds. These clouds are then passed to the radiation scheme where their radiative effects on the climate are calculated. And then you output these three-dimensional cloud fields and save them so that when you perform your cloud locking run, you still allow the model to make the clouds. However, when the radiation scheme is called, you input clouds from a reference run rather than putting in the clouds that the model itself is making. And in this way, you kind of you decouple the clouds radiatively from the climate system. So this would be very helpful, for instance, if you were trying to quantify the cloud effect of climate sensitivity, if you were doing like an abrupt 4x CO2 case or something. And you can also perform cloud locking regionally. So instead of cloud locking everywhere and prescribing clouds over the entire globe, you can only perform cloud locking in very specific regions. So if you were interested, say, in only studying Arctic cloud feedbacks, you would then cloud lock only in the Arctic. The radiation scheme in CAM requires 9 3D cloud variables, and you have to prescribe them every 2 hours because that's how often the radiation scheme is called. 5 of these variables are physical variables like cloud fraction and liquid water path, et cetera. And then 4 are microphysical parameters. But the question that we're asking here is very specific. We want to know if in the most dramatic case, this 100 watt per meter squared change in cloud forcing over 6.5% of the globe, if it can cause 8 Kelvin of global warming. So we actually can't do the standard cloud locking. We're going to do something called synthetic cloud locking. So what we're going to do is perform 4 cloud locking runs, 2 at high CO2 and 2 at pre-industrial CO2. And at each CO2, we'll have a locked strato run where we prescribe very strong stratocumulus clouds, and we'll have a no strato run where we completely remove the stratocumulus clouds to quantify what the climate effect is of such a breakup. And so here what I'm showing you is just an example of what the shortwave cloud forcing would look like between a strato-locked run and a no strato run. You can see in these regions I've prescribed really strong stratocumulus clouds with shortwave forcing of, on average, 100 watts per meter squared. And then down here, I've completely removed them. So there's practically no shortwave forcing in that case. So I'll kind of walk you through a little bit more exactly how this synthetic cloud locking works. So first, I just define my region of cloud locking. Like I said, we're interested in these subtropical stratocumulus cloud regions. So we center our cloud locking regions around observed areas on Earth where we see these stratocumulus clouds. And then we make sure that our regions total 6.5% of Earth's surface. And then we also note that these are low altitude clouds. And so we're only going to perform cloud locking in the bottom 10 layers of the atmosphere. And this means that high altitude clouds are still allowed to evolve and are still radiatively coupled to the climate system. And then we still want to capture things like seasonal and diurnal variability. So we also are going to prescribe a temporal variation in the cloud parameters. The first thing that we noted was that these are liquid phase clouds. So that actually greatly simplifies the cloud locking scheme right off the bat. We only need to prescribe cloud fraction and liquid water path, and then 2 microphysical parameters that describe the size distribution of these liquid water droplets. Based off of observations, we approximate the seasonal and diurnal cycles as sinusoids. And here's an example of the synthetic temporal variation of these cloud parameters. So this is the seasonal cycle, and then on top of it, we put a diurnal cycle. And then the last thing we need to do is have a vertical profile for the cloud fraction and liquid water path. So essentially, we just took a control run from CAM6 and normalized how cloud fraction changes with height in a subtropical stratocumulus region. And what we do is we then just multiply this normalized vertical profile by whatever the temporal value of the cloud fraction or liquid water path is at that time. And now we have our 3-dimensional cloud field. And we put in the same clouds at every region. Here's just a brief summary of what this synthetic regional cloud locking method looks like. There are 2 perks to doing this kind of cloud locking versus the standard cloud locking. The first is that we're putting in clouds that the model actually can't make on its own. So we have a lot of freedom in designing exactly the kind of cloud with the exact radiative forcing that we're after. And also, we're able to write all of the temporal variations analytically, which means that we don't have to read in 3-dimensional cloud fields every radiation time step. We actually just hard code the synthetic clouds into the radiation scheme. And this saves a lot of computation time. So for example, there's no computational difference between a standard CESM run and a CESM run where you're doing this synthetic cloud locking method. Okay, so we are going to perform these cloud locking runs at 8x CO2, and we spun up the model using the paleo calibration that's defined in Zhu et al. 2022. And basically what this does is it removes an inappropriate cap on ice particle number, and it decreases the microphysics time step. And this calibration had a lot of success in recreating the LGM in CESM2. So we perform a fully coupled 2-degree run using the paleo calibration. And in our 8x CO2 world, we have a global average surface temperature of about 29 degrees Celsius. We've completely melted all of our sea ice. It's a much warmer world for sure. So that's what I'm showing on the left. And on the right, I'm plotting a histogram of the daily minimum winter surface temperatures in northern US. So remember, we're interested in trying to figure out how we could have above freezing temperatures always in the interior continent. So in the green, that's the control 1x CO2 case, and then the red is our spun up 8x CO2 case. And you can see we've made a lot of progress. We've shifted this distribution way to the right, but there are still plenty of below freezing temperatures. So now is the time to ask if the breakup of stratocumulus clouds can get us the rest of the way there. So here I'm showing the same plot, but what I'm showing is in our 8x CO2 case, we have this strato-locked version where I'm prescribing very strong stratocumulus clouds, and then in the pink, it's the no strato version where I've completely removed these clouds. And you can see that removing the rest of the stratocumulus clouds does shift the distribution in the right direction. So I think this is a helpful feedback, but there's still plenty of these below freezing days in the interior continent. So this is maybe suggesting that, at least with this version of the model, the stratocumulus breakup can't on its own solve this puzzle for us. But like I said, we're also interested in just globally what a complete breakup of stratocumulus clouds would look like. So remember, this back of the envelope calculation is kind of the motivation for us. So what I'm showing here is the annual zonal change in surface temperature as a function of latitude. And I'm showing it for 2 of our cloud-locked simulations. So the blue is in a 1x CO2 case when I take out all the clouds versus when I have very strong clouds in the subtropics. And then the red is in the 8x CO2 case where I do the same thing. So you can see that the global average temperature change in both cases is at most maybe 4 degrees Kelvin. A lot of the warming is isolated to these low latitudes. You can see these shaded regions. I'm just reminding you what latitude bands I'm performing this cloud locking at. And then since we're also specifically interested in what's going on over land, I'm plotting the same figure, but I've isolated the plot to only over the continents. So you actually get a bit more warming in the 8x case, maybe 4.5 degrees Kelvin, but it's still not quite as high as the 8 Kelvin estimate. And then here I'm just showing you a 2-dimensional map of the surface temperature distribution. So I've put contours around the regions where I'm performing cloud locking. And again, I mean, you do see very strong warming that is specifically in these cloud lock regions and very close to it, but the global average warming that you see is only up to about 4 degrees Kelvin. So to conclude, even in the most dramatic case, remember we designed this experiment to kind of give this theory the best shot. Even in the most dramatic case of a 100 watt per meter squared forcing over 6.5% of Earth's surface, the subtropical stratocumulus breakup only causes 4 Kelvin of global average warming, which is still a lot. So this is clearly an important cloud feedback. And then we also showed that in the 8x CO2 scenario, even completely removing the rest of the subtropical stratocumulus can't on its own mitigate the below freezing days in the continental interior. But now that we have this synthetic regional cloud locking method, the rest of my thesis is going to be applying it to other cloud feedbacks that have been suggested to be relevant during the Eocene. And we're hoping to see that maybe some combination of these cloud feedbacks that aren't as well represented in the climate models today can kind of work together to help explain these warm continental interiors. And I'll take questions. Thank you.
Thanks. Great talk. Do we have questions? Yeah.
Yeah, this is Sophia. I noticed that in your maps, it looks like you're using just a modern land configuration. And so I was just wondering if these were kind of just a CO2 increase exercise to emulate Eocene levels, or if you made other changes to the simulations to kind of account for maybe differences in land surface cover. And I'll keep it there.
Yeah, no, great question. Yeah, so we did the simplest thing we could think of, and you're right. This is essentially just Earth with 8x CO2. We changed nothing else.
Okay. And I guess the follow-up is just that, do you think there could be other modifications you could make to the land surface to emulate Eocene boundary conditions that might influence the effect of this stratocumulus breakup on temperature?
Yeah, definitely. I mean, I think that like even just including vegetation that is kind of more similar to the Eocene could kind of push us more in the right direction. I think that the kind of first stage of this project was just to quantify in a high CO2 scenario what kind of climate sensitivity can you get from changing the stratocumulus clouds. But yeah, the actual connection to the Eocene I think would require a more careful change in boundary conditions.
Thank you.
Okay, we have another online question. Michelle?
Hi. Yeah, I was just curious. You said you're gonna look at some other cloud feedbacks. What other cloud feedbacks have been proposed to be significant during the Eocene or other hothouse climates?
I'm so glad you asked. Thank you. So yeah, I mean, there's many. I think that the ones that have drawn a lot of attention, especially in the past, are the ones that actually occur at high latitudes. So I listed a few here, but I can go through them. So for example, polar stratospheric clouds are very high altitude clouds. So if we had more polar stratospheric clouds, that could perform a lot of like long wave greenhouse warming. And kind of similarly with Arctic convective clouds, these clouds could occur in polar night and be very high altitude and provide a lot of greenhouse forcing. And then these low continental clouds, what they do is they kind of like trap heat and don't allow these cold air outbreaks to get really, really cold when they come in to the interior continent. And that could really be key for minimizing these below freezing days that are kind of climate extremes in this region.
Okay, so generally you're just looking at different cloud feedbacks that we know could lead to
Yeah.
warming. I guess there's not really any evidence in the EOC of what is going on in the clouds.
Yeah, exactly. These are like theorized cloud feedbacks that might be relevant.
Right.
Yeah. So this is, yes, exactly.
Are you looking at aerosol impacts on clouds at all? I remember that being a topic for Pliocene climates, which I know is totally different than the Eocene.
No, I mean, definitely like once you get into microphysics, I feel like it's like it becomes even more of a mess. Right now, we're not even touching stuff like that, but no, I completely agree with you. I think that's definitely relevant.
Cool, thank you. This is really interesting.
Thank you.
We are going to take one question from the room first. Dave.
Yeah, Andrea, this is Dave. The talk was really cool. I guess I just have a question about the technical aspects. Like you said, you fit in an analytic model to like what the stratocumulus cloud should be. And I guess climate models have a huge bias in stratocumulus clouds relative to observations. Are you fitting that model to like observations and then putting that in the model, or what's the kind of methods you're using?
Yeah, so for the temporal variations, we're fitting those to observations. And like I said, like it's a very simple way to represent it. We're just making it sinusoidal. For the vertical distribution, we are taking that from CAM, but
Okay.
also, I mean, that's also pretty simple. It's pretty much no cloud, you got a cloud layer, and then there's nothing
Yeah.
about it. Yeah, I mean, I want to emphasize that what we did is like pretty crazy. I think the thing to take away from this talk is that what we were really interested in is like that specific radiative forcing in those specific regions. If you
Yeah.
do that, what happens? It almost is less relevant exactly what the details are of how you get there.
Okay. I was just wondering if you put in like a vertical profile of stratocumulus cloud fraction from observations, do you think that would change the story much?
I don't think so. I mean, I really think that if the radiative forcing was the same, it wouldn't really change our results that much. But yeah, I mean, if there was like an easy way to make it match observations better, we would certainly be interested in hearing about it.
Okay, thanks.
Okay, Paul, you can go ahead and ask your question.
Thanks. Great talk. So there's no proxy for clouds, but you can kind of see SSTs as like some type of measure of that. For your runs, your boxes are over the upwelling regions.
Mhm.
Like, how does that change, the circulation over those upwelling regions?
Yeah, that's a great question. Yeah, so I mean, the subtropical stratocumulus clouds preferentially occur over the upwelling zones because they really like having cold water beneath them. I am not an oceanographer, so I can't answer that question fully, but there's a person in my group who is really interested in like the shortwave forcing feedbacks on upwelling and how there's like some sort of climate connection between the two. So we are not currently exploring that in this project, but I definitely think that that is interesting and relevant to things like the Pliocene, Pleistocene.
Cool, thank you.
And we still have questions? Oh, time for questions? Maybe I can ask a quick one. I think you are running the simulation in fully coupled mode, right?
That's right.
Whether ocean circulation can impact regional temperature at least.
Yeah, so we are doing a fully coupled run. We do see some interesting features that I think are related to especially like overturning circulation. So like in our pre-industrial run, for example, we actually see cooling in the Atlantic when we take out the stratocumulus clouds. And we actually end up kind of transiently collapsing AMOC in that scenario. So that was pretty interesting to see. That doesn't happen in the 8X case because AMOC is pretty much collapsed already at that point. But yeah, we ran this fully coupled version of the model to kind of allow the maximum amount of transport to the higher latitudes. So that was definitely on purpose.
Thanks. Quickly follow-up question about the AMOC in the 8-time CO2 simulation. You mentioned it has already been collapsed. I'm wondering, do we have a like active AMOC, or should we expect a sluggish circulation under this amount of high CO2?
Yeah, I mean, I think it would depend on who you asked. But I think that I think that the idea of having a sluggish AMOC and a high CO2 case is not super surprising, but whether it's model dependent, I think is definitely still up for debate. And I wouldn't ever claim that we absolutely should have a collapsed AMOC in an 8x CO2.
Thank you.
Mm.
Okay, we'll move on to our next talk from Michelle Dvorak. You flop the slides. Oh, sure. You can go ahead. Next.
The top is perspective. Yeah. It's been on the side for a while. I don't think I'll do anything. No, they only, no, I shouldn't have. They only had to go to like, yeah, whereas like, yeah. I think that just has to do with like when you have land, you've reduced the amount of water vapor already in the atmosphere. Yeah. So then you're just starting from a lower base state. Sort of like simplification stuff. Like the details of radiation can come yeah, I don't know if it's the radiation thing. It's just like well, a little bit of the issue. I think it's mainly like you don't have land. Yeah, it came about because like one day Tapio was like precipitation should always saturate, and I was like, no, it'll decrease, and then I was improve it. And then I would never do anything with it.
Well, sure, I don't know the. Oh, email. Oh. Yeah, should be
I was like, what is that?
Sorry.
GD gas. Maybe it's not on. I won't have your slides. Oh, that burden.
Unfortunately.
Work with these permissions.
So funny this.
Oh, cool, that advanced.
Just feels like you have.
Right, but we're kind of in such a order of the way
Yes. I'm just to log out and log in.
Guys, wake up.
It's
Both were up.
Yeah, okay. Hey, Vince, do you want to give yours? Because this isn't working. Share right now.
Sure.
Sorry for the technical problem. and maybe we can let Vince present first, and we will get back to Michelle's presentation.
Do you want to try to?
She can email the slides to that computer. You're able to share your screen?
Oh, I just used down
Which browser are you using?
Oh,
You have to go into your permissions.
Yeah.
Chrome, but not Firefox.
Okay. Were you using Firefox?
You can also try to bring them to my email.
But you can check your permissions. It's in here.
Yeah, I did check the permissions.
Did you?
Yeah.
That's where I had trouble. I was trying to, I know I can do it in Chrome, but when you can do it in Firefox.
Google Meet doesn't like the competition.
No,
Firefox.
you have to set them all up.
Okay, sorry about that. Thank you everyone for your patience. And we will have Vince presentation first. So Vince Cooper from UW, go ahead.
So thank you, everyone. Excited to be in card here today. I'm a grad student at University of Washington, working with Kyle Armour, also Cecilia Bitts and Greg Hakem. Before I jump in, I just want to say that this project has been a really big group effort. It's been fun to collaborate with people at different modeling centers and different data simulation groups. It's fun to work with such a big team. For a brief background and introduction, as a reminder, equilibrium climate sensitivity is typically calculated as the forcing from CO2 doubling divided by the feedback from the CO2 doubling. And recently, the Sherwood et al. 2020 assessment made some progress in constraining climate sensitivity, and that also informed the IPCC AR6 report. And what they did is they quantitatively combined lines of evidence for ECS, first looking at the historical records, that's changes back to 1870 or so. Then they also looked at process understanding of how individual feedbacks in the climate system operate. And then they turned to paleoclimate, and they looked at the Pliocene for evidence from a past warm period, and that's what Michelle will also be sharing some information about. And then they turned to the last glacial maximum for information from a past cold period. And after they combined these lines of evidence into a PDF of climate sensitivity, they found stronger constraints than some past studies. And a highlight that's relevant to this group, at least, is that it was really the paleo evidence that ended up being the best constraint for high values of ECS. And they specifically highlighted the LGM, for example, for helping constrain the likelihood for ECS above, say, 4 degrees, for example. Before we jump into the paleo data, though, I think it's important to turn a little bit of our attention to the historical record, specifically at why the tail for ECS in the historical record is so high. And I'm showing on the upper right here the climate sensitivity inferred from the historical record with and without this thing called the SST pattern effect. And the pattern effect is typically quantified as a difference in feedbacks that's caused by differences in the pattern of sea surface temperature anomalies. So what has been found is that the pattern of sea surface temperature change over the historical period produces this strong negative feedback, whereas the SST pattern that we expect from the long-term response to CO2 doubling has a more positive feedback. So that's the difference in feedbacks in the left here. And when you account for that, you get higher estimates of modern warming from the historical record line of evidence. For a little bit of physical intuition on how that pattern effect works, I'm showing this plot here, the global mean top of atmosphere radiation response to local sea surface temperature changes. So the blue regions here are where if we increase local SST a little bit, you get a strong negative feedback, so more efficient cooling to space, which stabilizes the climate. Whereas if you warm the SSTs a little bit in these red regions, you get a positive feedback that amplifies the climate change. So imagine reducing low cloud cover and letting in even more sunlight, which then further heats up the planet. So the relevant piece, or the especially relevant piece for the paleo record, is that the feedbacks tend to be more positive at higher latitudes. So any SST change that's outside of the blue regions tilts the scales towards a more sensitive climate. And that's something that we'll find for the paleo record, where temperature changes tend to be amplified at the higher latitudes. So the main focus for this work is are there pattern effects in the paleo evidence for climate sensitivity that have not already been accounted for? And for that, we'll look at both the LGM and the Pliocene. And for an illustration of kind of how climate sensitivity or feedbacks are typically inferred from the paleo record is normally you take all the different forcings. So for the LGM, for example, you add up the forcing from ice sheets, CO2, et cetera, and you divide by the global mean temperature change, and that gives you an estimate of the feedback. But then what we're asking is, before we use that LGM feedback to constrain modern day climate sensitivity, do we need to make an adjustment for how the feedbacks are different because of different sea surface temperature patterns at the LGM compared to what we expect in the modern day? The reason why we think there might be a pattern effect for the LGM and the Pliocene is because of the differences in the spatial patterns of forcing. So on the left here, I'm showing the relatively uniform forcing that we get from a CO2 doubling in the modern climate. And then in the middle now, I'm showing the forcing from the last glacial maximum, which has reduced greenhouse gases. And you can see that kind of uniform background forcing from things like lower CO2 levels. But we also have these really strong localized forcings from the ice sheet changes. So you can see the Laurentide in bright blue there. There's not shown in this figure is also the vegetation and dust and aerosols forcings, which are important, but and we account for those in our ECS calculations. They're just not in this particular plot from the model simulation. The Pliocene forcing is somewhat kind of similar, but opposite sign to the LGM in a way. There's not only the background forcing from greenhouse gases again, but we also have smaller ice sheets for Greenland and Antarctica. And there's also enhanced vegetation, which is included in this simulation over most of the northern high latitudes and also some of the tropical kind of desert regions, the Sahara, Arabian Peninsula. So we think that these different spatial patterns of forcing should cause different sea surface temperature patterns and then different feedbacks. And where the sea surface temperature patterns come from is a combination of model experiments and then also reconstructions. So on the left, our best guess for what the equilibrium response is to CO2 doubling comes from the long run MIP simulations, which Dave introduced, I guess, a talk or two ago. And then for the last glacial maximum, I'm showing the mean of 4 different reconstructions that have been compiled over the past few years. And the thing to note here is all of these reconstructions agree on this extra cooling that occurs in the northern hemisphere extratropics. So both the North Pacific and the North Atlantic have extra SST cooling, and that's from a stationary wave response to the presence of the Laurentide ice sheet. For the Pliocene, we have a slightly different story, but similar in some respects. There are some kind of similarities with the CO2 doubling pattern. I should also note that these 2 reconstructions for the Pliocene are still preliminary, so they're not finalized yet. They might change as before these get published, but it's what we have to work with so far. What they do both show, despite their differences, is more amplification over the Southern Ocean than what we see in the modern day CO2 doubling alone. So this Southern Ocean amplification for the Pliocene and the Northern Hemisphere amplification for the LGM are the 2 main differences in the SST patterns to keep in mind. Before I jump into the feedbacks, I also just want to note data assimilation has already been brought up here, but one of the main advances that enables this work is that these SST patterns are not just from the coupled model experiments, but they also bring in proxy data to constrain the patterns. And my brief summary of how this works starts off with this equation representing the ensemble Kalman filter. And the framework here, I think, first starts off in a way that's pretty relevant for the CESM paleo working group. So the prior estimate of the climate state comes from model ensemble, things like the isotope-enabled version of CESM. So that gives us our kind of first guess of what either the LGM or the Pliocene might look like. And then we bring in proxy data. So this is work that's done by some collaborators of ours, not myself. For this, I'm showing the Pliocene. So we have proxy data from ocean sediments. For the LGM, you might also look at ice cores or pollen records. And then those proxy data are compared with an estimate of the proxy data that comes from the model prior. And that's where things like the isotope-enabled versions of CSM are particularly handy because you can compare the isotopes directly. And then to spread the differences in the data versus the prior across the rest of the climate state, we use the Kalman filter, or this is the Kalman gain, sorry. So the model covariance between the location of where we have the data and how that varies with the rest of the state shows up in the first part of the Kalman gain. And then the strength of the update is weighted by uncertainty in the prior and uncertainty in the data. So if you have more confidence in your data, you get a stronger update across the climate state. Most important thing to know is that we come out on the other side with an updated ensemble mean that accounts for the model prior and the data. And we also have an estimate of uncertainty on the other side. So we can propagate all of that through to our future estimates of climate sensitivity. So now we have the SST patterns, and we can start to think about the feedbacks again. So we start off looking at this global energy budget equation, which shows how the top of atmosphere radiation, N, is equal to a change in the forcing, say from things like CO2 doubling, plus the feedback, lambda, times the surface temperature change. But what we're going to do is take advantage of a framework in the atmosphere models where we can ignore the forcing term, because what we'll do in all of our simulations is hold the forcings constant and only change the lower boundary conditions, so the sea surface temperature and the sea ice that's prescribed. And in that framework, there's no change in the forcing, so we can calculate the feedback from just the change in the TOA radiation divided by the change in the surface temperature. And we do that using 3 different kind of simulations. So we can calculate a feedback from the CO2 doubling that's only from changing the SST pattern, and then a feedback from, or for the LGM and the Pliocene that's also only from changing the sea surface temperature and sea ice patterns. So we run first a pre-industrial baseline simulation in the atmosphere models that's using the late Holocene reconstruction from Osman et al. And then we run that pattern from long run MIP that represents the equilibrium response to a CO2 doubling. And then we run a few different patterns, all 4 of these different reconstructions and some N members from their ensemble for the LGM and also for the Pliocene. And that gives us a little bit of a spread in the feedbacks from the paleo record that come from uncertainty in the reconstructions. Now for the results, before I show our simulations, for reference, again, this is just the historical record feedback compared to the CO2 doubling feedback for CAM4, CAM5, and CAM6. So again, we found that past studies found that the historical record feedback is more negative than the feedback from a CO2 doubling. When we run our Pliocene simulations, we get more positive feedbacks. So that's true for both of the reconstructions in CAM4 and CAM5. We haven't done them yet in CAM6 since these reconstructions aren't final for the Pliocene. But for the LGM, at least, we get the same direction of change. So again, more positive feedbacks from the last glacial maximum SST pattern in both CAM4, CAM5, and CAM6. And what we do to put a number on what the pattern effect is we calculate delta lambda as the difference between the CO2 doubling, so the red bar, and the paleo feedbacks, which is the Pliocene and the LGM bars. And we get negative numbers, so negative pattern effects for all of the paleo periods. This is the opposite of what was found for the historical record. So for the historical record, they had a positive pattern effect that weakened constraints on modern day ECS. For the paleo record, we're getting a negative pattern effect, which points us towards stronger constraints on modern day ECS. Basically says that some of the aspect that makes the feedback more positive in the paleo record was from things that are not related to CO2 doubling in the modern day. It's things like losing the Laurentide ice sheet. So we want to make an adjustment for that when we infer modern day ECS. Before we make any changes, though, to the constraints on ECS, we want to make sure that we understand what the mechanism is. So what we found is the most important part of the mechanism is the shortwave cloud feedback that's caused by those non-CO2 forcing. So things like the ice sheet changes. So on the left, I'm showing a spatial representation of the feedback from cloud changes and the CO2 doubling first. And you can see kind of like the red regions are where there are more positive cloud feedbacks that amplify the change. In the middle now, I'm comparing with the same thing, but for the LGM. So for the last glacial maximum, you see these big red bullseyes over the North Pacific and the North Atlantic, which indicate a much more positive shortwave cloud feedback over those really cold SST regions. So those ice sheet induced SST patterns are amplifying the climate changes for the LGM much more so than what we see in the CO2 doubling. And we know again that those specific aspects of the LGM pattern from experiments in CESM are caused by the ice sheet forcing, not the CO2 forcing. For the Pliocene, similar story, but the location's a little bit different. So it's the extra SST amplification over the Southern Ocean that's causing the more positive feedback in the Pliocene compared to CO2 doubling. And Michelle's experiments help illustrate that, which she will share shortly, hopefully. Knock on wood. Okay, so now we know what the mechanism is, and we can start, or we can make our final, this is the final piece of the results here. We can actually update the ECS estimates that were provided in Sherwood et al. And propagated through to the IPCC report. So first, we start off with the feedback that was calculated from the Sherwood et al. Assessment for the Pliocene. We don't make any changes right now to the forcings and temperature change estimates that were in the Sherwood paper. What we do is we just add an adjustment to the feedback that represents the difference in feedbacks caused by different sea surface temperature patterns. So we're only adding this little adjustment term as our only change. And when we do that for the Pliocene, you can see that we get a little bit kind of a lower tail for ECS from the Pliocene. And what we do is we assign a distribution to that delta lambda term that's based off our model simulations, and it includes uncertainty from differences in model physics and uncertainty in the reconstructed SST patterns that's propagated all the way through to the ECS constraints. So we're kind of doing our best to make sure that all of the uncertainty is retained and propagated through to the ECS estimates. For the LGM, or sorry, before the LGM, what we can do after we've updated the Pliocene evidence is we can then combine that with all of the other lines of evidence for ECS that were included in the Sherwood assessments. That was the historical record and process understanding. And when we do that kind of synthesized combined PDF, we go from the gray box to the orange box here. So we get kind of tighter constraint overall just from making this one change to the Pliocene evidence. And then we can also bring in the LGM. So for the LGM, we have a bigger pattern effect because just the magnitude was even stronger. The Laurentide ice sheet causes such a big difference in the feedbacks. And when we propagate the LGM evidence and combine it with the Pliocene, we end up with this kind of blue box on the bottom. So around 2 to 4 degrees is the 5th to 95th percentile range. And just by comparing the gray versus the blue, you can see that including this paleo pattern effect gives us a much tighter constraint on modern day ECS compared to what we got without considering how sea surface temperature patterns are different in the paleo record compared to modern day. With that, I'll leave up my conclusions just to go over them briefly. The feedbacks were more negative in the modern day CO2 doubling than they were in the paleo record. That difference in the feedbacks was mostly caused by different cloud feedbacks, and those different cloud feedbacks are attributable to the non-CO2 forcing, so the things like the ice sheets and the vegetation changes rather than just the CO2 pattern. And when we account for that paleo pattern effect difference in the feedbacks, it actually helps constrain modern day ECS as opposed to blowing up the constraints, which was what was found for the historical record. And obviously these lines of evidence will kind of refine as different aspects get better constrained in the future, but we think that this one particular piece points to stronger constraints overall. And with that, I'm happy to take any questions, and I'll say that we've got a preprint available in case you're curious about the LGM work. Thanks.
Thanks for the great talk. Do you have questions? Go ahead. No.
And during the LGM, expect for the SST pattern changes, the sea ice pattern also changes.
Mm-hmm.
Will the sea ice pattern will also have like feedback that influence the sensitivity?
Yeah, it's a great question. So for brevity, I kind of focused on the sea surface temperature patterns and not the sea ice so much. But the reconstructions, 3 of them, not all 4, but 3 of the reconstructions also include reconstructions of the sea ice pattern. So all of the feedback differences that we've calculated also include those sea ice changes. So we didn't do something like hold the sea ice fixed and ignore that. The sea ice changes are included in this estimate. What we end up finding though, and why I didn't focus on them as much, is that a lot of the LGM sea ice changes that kind of make the feedback more positive actually occur kind of underneath where there are already a lot of clouds. So the effect is somewhat damped by cloud masking and isn't as strong as you might otherwise expect. So the SST pattern ends up being a bigger impact, but the sea ice is accounted for.
Yes.
Go ahead, Dave.
I guess I follow the whole like pattern effect and this like linear TOA forcing feedback framework. If you did, like, what is the role of a nonlinear feedback here? And is that encapsulated in this like delta lambda that's the pattern effect, or like, yeah, have you guys accounted for that?
Yeah, it's a good question. For the most part, I think like one aspect of non-linearity in the feedback, you could view it as the pattern effect itself. So that's one piece, but there's also the temperature dependence of the feedback.
Yeah.
And there's another thing that I talk about more in the paper, but not so much for this talk. So there's some dependence on the global mean temperature of feedbacks, and that's also included in the way that we've calculated delta lambda. So we've kind of added that nonlinearity into this delta lambda term, but that's another kind of factor. So we've kind of used this delta lambda as one more approximation to try to capture the way that feedbacks are kind of nonlinear depending on the state, whether that's the pattern or the global mean temperature. Thanks.
Okay, Betty?
Yeah, I'm fascinated, but I'm still digesting this all. But my question is, for example, the LGM and PMIP4, there were 3 different ice sheets people could have used with, I think I6G probably the largest, and one of the other ones not quite as tall. So that would affect your pattern in the North Atlantic, I would think, and your stationary. Have you thought about looking at those models that used one of these other ice sheets?
Yeah, so one of our reconstructions, I think James Annan, he led this one, looked at I think PMIP2, PMIP3, and PMIP4 to try to, they wanted to account for a lot of spread across different climate models and uncertainty and things like the forcing. So their prior that went into the data assimilation also included simulations that used different ice sheet configurations. To some extent, though, the proxy data are going to tie us closer to the right SSTs no matter what. So as long as the data assimilation is able to map onto the right pattern that's captured in the proxy data, the differences in the ice sheet forcing shouldn't mess with the SST patterns too much. However, there is another aspect where they would have an influence, which is the calculation of the forcing itself. My work here isn't focused on refining the forcing estimates, but the forcing is a key part of the calculation too. So accounting for uncertainty and things like the ice sheet height or cover is also a whole nother aspect that we could improve, is quantifying the forcing too.
So in the interest of time, I think we should move on.
Thanks. Thanks everyone.
Please turn on that screen.
Are we going to have Michelle's presentation next?
Oh, you have one? Oh, I have it on. Yeah, I got it on my computer.
Okay, so you can use
So
your-
can you stop sharing?
Yeah. The questions are even.
So please stick around and we will move on to Michelle's presentation next. Stop sharing here.
I have it right here. Let's see, it's sharing. Go to the window. Oh, here we go. All right. Oh, here, I'll put you right here. Right here. Those you want.
Okay. Sorry. Thank you for your patience, everyone. Also, where's that's the camera for the.
Yeah, but you can talk to whoever you want.
Okay, so I'm Michelle. I'm a graduate student at University of Washington School of Oceanography. This is quite similar to Vince's research. We're kind of asking similar questions about these pattern effect estimates for the Paleoclimate period. I'm particularly looking at the mid-Pliocene, and I'm approaching this from a modeling perspective. And in particular, I'm kind of asking why these SST patterns arise. So without further ado, I'll just talk about why and what of the mid-Pliocene. So this was a period in Earth's history about 3 million years ago, during which temperatures were approximately 3 degrees warmer than the pre-industrial, while CO2 concentrations were similar to today's, around 400 parts per million. And given the potential for global warming to reach similar levels over the 21st century, it's been widely used as an analog for future climate change. And as such, as a constraint on modern day climate sensitivity, which Vince talked to us about. So yeah, here I'm showing that Shorewood et al. 2020 estimate that relied on the mid-Pliocene to infer climate sensitivity. However, the Pliocene is not a perfect analog for future climate because it's characterized by some key paleo-environmental differences. Namely here, there's a large-scale reduction of the Greenland ice sheet, as well as complete loss of the West Antarctic ice sheet. There's also topographic differences, such as closure of the Bering Strait and the Canadian Arctic archipelago. And we also see wide-scale vegetation changes, like expansion of boreal forest in the north and changes in vegetation over Saharan Africa, etc. So how has it been used to constrain climate sensitivity? Back to this likelihood distribution. So this was calculated. So Vince showed how for the LGM, this was calculated using an estimate of the individual forcings present in the LGM, but those aren't really available for the Pliocene. So what has been done thus far is to take this estimate of forcing from CO2, which was quite small, given that the concentrations were only 400 parts per million, and inflate them by this efficacy factor, this FESS, which is kind of like a catch-all for the Earth system sensitivity. Meaning it's including the long-term changes associated with these ice sheet differences and vegetation changes in the Pliocene. From there, that combined with estimates of the temperature change in that climate gives an estimate of lambda, the global feedback during the Pliocene. Oops, I forgot my animations. Sorry. Okay, so the reason this is important is that this FESS is kind of vague, and the problem with using this construction is that those boundary conditions with the ice sheets and vegetation have been shown to have a large effect on the global temperature of the Pliocene in many climate simulations. So here I'm showing fully coupled CESM2 simulations of the mid-Pliocene, where we see that more than half of the total global warming during that period is attributable just to the boundary conditions. So the orography, the ice sheets, and the vegetation accounted for almost 3 degrees out of a total of 5.1 degrees of global warming during that period. This isn't just CSM2, CCSM4, we also saw a significant amount of warming coming from boundary conditions, represented by this offset between the orange and the blue lines of the Pliocene and the pre-industrial at constant CO2 levels. So this brings us to our research questions of whether this warming is a response to large forcings, or rather are there feedbacks at play that are enhancing the response to the boundary conditions. So to answer this question, we first need to deduce what the ERF, the effective radio forcing, actually is during this period. So to do this, we've run a novel suite of fixed SST simulations and using CAM6, where we've run 3 simulations analogous to those 3 figures I just showed, where we had mid-Pliocene with 400 parts per million CO2, then we had only the boundary conditions, which is the same except pre-industrial CO2, and then we had a CO2 only driven run. We ran them for about 35 years, and we've prescribed an SST and sea ice fields from the pre-industrial control. So like as Vince talked about, if you have the forcing constant and you don't allow the sea surface to change, you just calculate the forcing from the net top of atmosphere radiation, or net top of atmosphere radiative imbalance. So this one kind of interesting aspect of this modeling work is that because we don't have a West Antarctic ice sheet, and because West Antarctic ice sheet is actually marine grounded, where we've removed the ice sheet, we actually get these new ocean grid cells that aren't included in the pre-industrial control simulations. So the question of what to do with sea ice there, how do we treat SSTs where no pre-industrial SSTs existed, was an open question for us to answer. So we opted to set the sea ice concentration to 100% there, so that we would kind of best emulate the pre-industrial control shortwave radiative forcing there from the ice sheets. If you can imagine, the sea ice is pretty much similar albedo as a land ice. And consequently, SSTs are set to the freezing point of seawater and CSM2. So what does this give us? We are able to determine what the total radiative forcing is in the mid-Pliocene. We also can determine what it is just due to the boundary conditions, and we can compare that to CO2 only forcing. And what we find is that even though in the fully coupled simulations that boundary condition simulation gave us more than half of the total warming, its respective radiative forcing is quite a bit less than 1/2. So it's 1.7 out of a total of 3.8 watts per meter squared. Interestingly, we do get some negative radiative forcing here. The positive radiative forcing from these land surface changes stand out the most, but we also get slight negative forcing over the oceans. And we find that those are associated with low cloud changes. Okay, so moving on, now that we have the radiative forcing, we want to know what the feedbacks are. So from here, we ran a series of slab ocean simulations, also in CESM2. And we have a coupled atmosphere and a slab ocean with fixed mixed layer depth and ocean heat flux convergence, which we have diagnosed from the respective fully coupled pre-industrial control run. So here I'm zooming in on Antarctica because we did have to make this novel modeling choice again, where we've, in order to best achieve this kind of pre-industrial ocean heat flux convergence around Antarctica, we've opted to set ocean heat flux convergence 0 over here where we don't have that ice sheet anymore. But as you can see, it looks pretty much identical to the pre-industrial control heat flux convergence. So what we find from this is that the Pliocene and CO2-driven slab ocean runs give us really similar patterns of warming. However, the boundary conditions alone actually give us this interesting kind of La Nina-like pattern where we actually observe cooling over the Southern Ocean, as well as cooling in the Eastern Tropical Pacific. And as we know from recent pattern effect literature and from what Vince was describing, this is primarily due to these low cloud changes that amplify the cooling in these regions. And Yue Dong has some nice research that talks about the atmospheric teleconnection, where cooling in this part of the Southern Ocean here can result in cooling in the Eastern Tropical Pacific just by way of wind, evaporative, and SST feedbacks. So essentially, the background atmospheric circulation can advect these cool anomalies into the Pacific. Those lead to those low cloud enhancement changes, and that further amplifies the cooling. So interestingly, this results in pretty globally damped warming from the boundary conditions in these slab ocean simulations. Sorry, it's a bit difficult to see, but the boundary conditions are only giving us 1.2 degrees of warming, even though the full mid-Pliocene is around 4.5 degrees of warming. And yeah, these are not additive here. That 1.2 and 2.5 degrees aren't giving us the same, the total warming of the Pliocene, which suggests that there are different feedbacks at play between the non-CO2 and the CO2 forcing, if that makes sense. To investigate this phenomenon a little bit further, here I'm showing polar projections of Antarctica, where we see this air temperature anomalies in the boundary condition simulation, where we have this broad cooling over the Southern Ocean. And I'm just showing these some interesting wind vectors. So these are surface wind anomalies that arise because of these topographic differences, where you have this flat West Antarctic or absence of the ice sheet there. This leads to an enhancement or growth of sea ice in that area, which can further cool the sea surface through the sea ice albedo feedback. And I just want to point out that other idealized lab ocean experiments where they've flattened that Western Antarctic topography have also given us broad cooling as a result of this kind of cyclonic wind anomaly. It's a bit difficult to see here, but these wind vectors are kind of advecting equatorward from the polar cap. Okay, so to compare this with the fully coupled simulation, it's, well, it's not too different in our full mid-Pliocene and CO2 simulations. Certainly when we just have the boundary conditions, the fully coupled simulation gives us much more warming and overall very similar SST patterns across all simulations. So this is telling us that the active ocean dynamics in our fully coupled model are essentially acting to really counteract that cooling or warm that sea surface up, and probably through the same atmospheric teleconnections leads to that warming in the tropical Pacific as well, and overall much higher global warming and similar patterns of SSTs across between the CO2 and the boundary condition cases. Consequently, the global temperatures rise as a result, and we get more linearity between the global temperature responses. And just to highlight that, this is a differences plot from of the normalized SSTs between the fully coupled and the slab ocean simulations, which show significant warming in those key areas I mentioned. Okay, so why is that? Well, in these fully coupled simulations, we can look at heat transport. And just briefly, I'm going to point out that in the pink and blue lines, so the mid-Pliocene and the boundary condition cases, we get significantly more southward heat transport, south of 65 degrees south. Just back of the envelope calculation, this 0.1 petawatts of heat distributed over the polar cap south of 70 degrees would give us about 6.5 watts per meter squared of forcing. So it's really significant and can help explain why it's so much warmer in the fully coupled model than it is in our slab ocean. 2 more minutes. Thank you. Okay, so from here, we're going to just calculate our global feedbacks. So Vince did a nice job explaining how we can do that using the standard framework for energy balance. Here we find in our slab ocean model that we get significantly more negative feedback, global feedback associated with our boundary conditions. However, when we have these active ocean dynamics, the global feedback is much more positive, and we have much more consistency between our mid-Pliocene and our CO2-driven simulations. I'm going to skip that. Just another differences figure, and just showing how important these ocean dynamics are in shaping the magnitude of the global feedback. Okay, so all that is to say that, yeah, accounting for the differences between the feedbacks associated with carbon dioxide and those associated with these boundary conditions essentially reduces our estimate of modern day climate sensitivity where we're using the Pliocene to constrain it. So it's kind of nice where even in our slab ocean model, we don't see a large pattern effect because yeah, so those feedbacks were quite similar between the Pliocene and carbon dioxide burst runs. In our fully coupled model, we're arriving at a pattern effect estimate that's actually quite similar to what Vince was showing with the data assimilation approach. And just to kind of go back to echo what he was showing here, is that we do get these more positive cloud feedbacks here in the Pliocene than we do in our CO2-driven case. So yeah, back to this equation. What we've done in this study is that we don't really need to calculate it using this efficacy factor. Rather, we actually have quantified the forcing, and from there we get a more precise estimate of the global feedback. Okay, thanks very much.
Thanks for the new talk. We have questions. Maybe I could ask one.
Yes.
I agree with your approach of using a zero ocean Q flux for in the Antarctic, and I think makes physical sense. But I'm wondering whether you have tested the alternative way of treating the ocean heat flux besides using zero.
Yeah, that's a good question. I might pawn that question off onto Ran because she I believe did run a slab ocean simulation where the Q flux was I think it was like linearly interpolated from like nearest neighbor approach.
Yeah.
And correct me if I'm wrong, Ran, but I don't think we observed quite as much cooling in the Southern Ocean as a result.
Oh.
One thing that we're doing next is I wanted to see if that see what the role of ocean circulation was in that region. So what our next simulation here that we've done is I've taken there's a line south of 65 degrees south where I'm imposing the Q flux from the respective fully coupled simulation to see if that kind of changes that cooling response. I also wanted to see if that it was the cooling in the Southern Ocean that then gave way to the equatorial Pacific response in order to kind of clarify that relationship.
Yeah, thanks.
Thank you.
Okay, do we have more questions? Okay, let's thank Michelle again.
Yeah, who's cheering?
Oh, yeah. All right. Okay, we're gonna start our last session of the afternoon. Can everyone online hear? Okay.
Yes.
Okay, great. We're gonna start with our first speaker, Betty Otto Peacer.
Okay. So yeah, I want to talk about some high resolution CSM simulations we're doing, in particular talk about some analysis that Esther and I have started looking at the tropical cyclones, mainly just the statistics now, but a lot more interesting. I just want to acknowledge the first line of people there, Jean, Ren, Clay, and Fred, who's an oceanographer, the ones that actually ran these simulations, set them up, babysat them, ran, figured out what was going wrong. You see a whole list of people that worked with us on kind of the design of them. And then I wanted to include there in the bottom line, Jim Edwards, who's one of the software engineers here, who's critical in terms of the porting, testing, debugging, even optimizing things. Ulrich provided a lot of consulting on some of the extremes package we used. And then Nan and Tegan have been working with us on the post-processing. So the way this came across was when we get a new computer here at NCAR, in this case, supercomputer Duratio, which is up in Wyoming, they allowed people to propose running some very large simulations before they released the computer to the rest of the community. And so we were awarded one called Extreme Weather Events under a wide range of climates and high resolution coupled CSM. They gave us 74.4 CPU core hours on Duratio. The thing is, we had to use it in 3 months, so June, July, and August, but we succeeded. And what it really allowed us to do is to look not only at things like mean and seasonal aspects of climate in the past, but also, for example, extreme rainfall events, and eventually, hopefully, to work on interpreting what the geologic records mean. So the simulations we ran a what I call warm house, the Pliocene 400 ppm. We ran kind of two kind of more extreme climates, the LGM with 190 ppm, an ice house climate, and a hot house, the Eocene, where we actually ran two different carbon dioxide levels, 3 times pre-industrial and 6 times pre-industrial. And we also took advantage of some other simulations that had already been completed as part of this IHES project. They have historical and some RCP and a PI, so we could take advantage of those simulations. So in terms of the model configuration, we used the code from this trilateral partnership of NCAR, Texas A&M, and Qingdao called IHESP. So the I here doesn't stand for water isotopes, but it's a 1/4 degree atmosphere land and a 1/10 degree ocean and sea ice. And these are global coupled simulations. And if you want to see more about their simulations, you can look at this James publication. We included and added water isotope capability. And just quickly, hope it's not on, it's getting done. For the ocean grid, since the grids are very much sometimes tuned or adjusted, we actually adopted the same ocean grid for the LGM and Pliocene for the Eocene because of the continental configuration. This is a tripolar grid. We had to move the 2 north poles, or rather Jean had to remove them. Everything else, paleogeography, vegetation and such, follow the PMIP4, PLIMIP2, and DeepMIP. Key is even though that sounds like a lot of computing resources, it was only enough to run about 60 to, in one case, 100 years. So you can't spin up an ocean, so we started from spun up low resolution simulations. And this just shows you kind of an illustration of the spin up LGM, pre-industrial Pliocene, and the Eocene 3X in the high res and solid and the low res we started from. And you can see they're relatively well spun up in terms of global mean temperature in 60 years. The 3X is a little bit warmer, maybe about a degree or 2, though looks relatively stable by the end of 60 years. In terms of the analysis we did, we used 2 different extremes packages. One's called Tempest Extremes and the other one's called CMIP. And we have 6 hourly instantaneous output from these simulations. So I'll show you the last 30 years from these 4 ASD simulations, which I just showed you are approximately in equilibrium. And then we also, Fred Castruccio made available to us 2 of their RCP 8.5 future simulations. So looking, I do terribly with this mouse, at the last, or close to the last 30 years, 2066 to 2095. So just looking then at some results, this is from Tempest Extremes. On the top is the observed from the IB tracks. So it's 1980 to 2016. It's kind of an historical data set where they took a lot of different data sets and came up with one kind of data set combining all those. And the genesis density is just telling you kind of where the storms were generated. So they're first entry of an individual storm's time. So you can see here on the top is that, and the bottom is our high-res pre-industrial. You can see the model does pretty well. Maybe I won't point anymore. Does pretty well in the Eastern Pacific. You see the observed shows a large magnitude of genesis there that the model captures, and also kind of in the Western Pacific and into the Indian Ocean in the Northern Hemisphere. Also a band of in genesis in both the observed and the model along the Indian Ocean and extending into the southern Pacific, and then storms being generated, particularly coming off of Africa and onto the east coast of North America. So then just some results looking at the ASD simulations. The top left is the pre-industrial again, genesis density. If we look at the last glacial maximum, that top panel there, you can see decreased tropical cyclones being generated in the North Atlantic, but otherwise broadly similar in the other basins. If we look at the Pliocene there in the middle right, and then the two RCPs, you can see increased tropical storms being generated here in the North Atlantic, but decreased here. It's hard to see here, but I'll take my word for it, that in the Eastern Pacific and the Southern Indian Ocean. And then if we look at the two Eocene simulations, here are the 3 times CO2 and the 6 times CO2, you see increased genesis here again in the North Atlantic, though interesting, it's kind of cut off or restricted here right along the low latitudes, increased also in the South Atlantic, a poleward expansion in both of these of where we generate storms as compared to present, and also more storms being generated here in the Eastern Pacific. In terms of tropical cyclone tracks, again, the top is the observed and the bottom is the PI simulation. In terms of global average annual number, it's about the same between the two. We do well on that. Also, in terms of the Cat 1 through 5, 41 in IB tracks, 43 in the high res. But you can kind of tell here by looking at the maps, those darker reds are category 4 and 5. And you can see that they're underestimated in the high res PI, possibly because it's pre-industrial, but IHESP also found that's true in their simulations. And so this just shows the historical tracks again, and just a few things to note. Again, there's for the if we just start with the Eocene here, you can see there's fewer tracks in the tropics. We can see that in the Eocenes, the tropical cyclones extend to higher latitudes. Again, you see that there's kind of a dearth of tropical cyclone tracks here when you have 6 times CO2 versus 3 times CO2. If we look at the Pliocene here, you see the Pliocene and the RCPs are relatively similar in terms, both have a poleward extension of tracks in the North Atlantic. It is interesting, this has been noted in other works, that if we look closely here at the RCP 8.5s, you have more storms that are likely to form and traverse close to the eastern US. LGM has very few tropical cyclone tracks in the North Atlantic. We have a lot of sea ice. It's also much colder, and so that kind of diminishes the number of tracks there. And this just compares then the actual different categories among these different simulations. The black is the PI, gray is LGM. That's the Pliocene, the orange and red are Eocene, and these more purplish are the RCPs. And in particular, if you look at kind of the stronger storms here, you see that LGM has much less Cat 3 storms and no Cat 4. Actually, I think it gets, well, it gets 1 Cat 3 storm per year. The Pliocene and the, we'll look up here, Pliocene and the RCPs actually get 17 to 25% more Cat 3s and very few number, but maybe 3 to 5 times more. But these are statistics of small numbers here. And it really intriguing here if we look at the Eocene, so this orange and this red here, you can see that there's quite a bit more Cat 3 storms when it's 3 times CO2 versus 6 times CO2. So the fact that the low latitudes in the North Atlantic are hostile to tropical cyclones means much diminished, even though we have much higher CO2. So just finishing up, just 2 interesting things, just coming back to the Eocene here with the 3X on the bottom and the 6X. Tropical cyclones and climate have these feedbacks, and you need this high potential intensity humid troposphere, but also low shear. And what has been found in other studies, both Fedorov with some idealized aquaplanet, also some work that Jeff Keel did where he had fixed SSTs, is that the vertical wind shear, which affects the vertical extent of convection to main, so you need low shear to maintain convection or strong to inhibit it. There was an increase in shear in this location, so it kind of topped it off why it allows, there's lower shear as you get farther north. One last result, I guess I'm doing okay, is some additional runs that Jiangsu completed for several of the runs. In particular, remember the high res had a 1/4 degree atmosphere and a 10th degree ocean. What if you have the same atmospheric resolution, but you only have a 1 degree ocean resolution called high res and mix R? So this shows the pre-industrial on the left here and the Eocene on the right. The top ones are the high resolution and the bottom ones are the mixed R. And you can kind of already see it just looking here. We have stronger storms, more intense in the Eocene. Also, that's true in the pre-industrial, though not as noticeable when you have a low resolution ocean underneath the high resolution. And that's really kind of noticeable here if we just look at the categories here. Category 3 in the high resolution are much less than the mix for the pre-industrial. And you can also see it also for the Eocene in particular for category 4. There are very few category 4 in the high resolution and a very large number in the mixed resolution. So this, this has intrigued us, but we haven't had really enough time to look at it. But, some possibilities are when you have high resolution, you have mesoscale eddies, and this leads to colder wakes, why you might more cold wakes, why the mixed resolution might have weaker cold wakes as a tropical cyclone passes. Could be associated with mesoscale air-sea interactions, which aren't as well resolved in the mix R. And it could be related to differences in latitudinal SST gradient. But it really is, I must admit, counterintuitive that when you'd have a lower resolution ocean, you'd have stronger, though there's been a lot of work by others here at NCAR looking at different aspects of this, though never in a coupled simulation like this. So just concluding, just some kind of high level, we basically looked at the statistics, but the high resolution pre-industrial came here as well in terms of global annual numbers of tropical cyclones, so it underestimates Cat 4 and 5. The last glacial maximum, we had fewer and less intense tropical cyclones in the North Atlantic. And the warmer climates, Pliocene, RCP, future scenarios, and Eocene, you see an increase in the number of intense storms and a poleward expansion to middle and high latitudes. Next steps, we really want to understand why and what. So why did the deep tropics become hostile to tropical cyclone genesis in the Eocene 6 times carbon dioxide Why not so in the 3 times? Why does the 1 degree mixed R have more intense tropical cyclones than the 10th degree? And of course, we really want to tie this to what records could be available that might indicate things about tropical cyclones during the past.
Questions? Yes, Mohammed.
Thank you so much for the great presentation. So I was wondering whether these high-resolution simulations are available for the research community and also for NCAR stops. And if it is available, then who would be the person to contact?
Yeah. So I think John's going to say a little bit more about the code, but the actual IHAS simulations, so the ones done by that partnership and the RCPs are available already, and you should be able to find those. Though I'm not sure how easy they are to find. Fred Castruccio would be the person to talk to. The Paleo, the ASD, we haven't released yet. So we're analyzing them. You can imagine just trying to get the diagnostics out at that resolution. So we want to make sure they look okay, but we're hoping to release those later this summer.
Okay, makes sense. Thank you.
And then Clay?
Hi, interesting results. Thanks, Betty. I was just curious, in some of the stuff we had done with fixed SSTs, we found a decrease in tropical cyclone intensity at the LGM, but not nearly as pronounced as yours. And I was wondering if, maybe for the Eocene runs, if you're also considering any fixed SST simulations as a further comparison of what's really driving the differences in tropical cyclone intensity.
So are you asking about other time periods per se, or
Yeah,
just...
so I mean, you did the Eocene. I mean, you could do it with the Eocene or another one. I was just curious, maybe some of the differences are actually due to somewhat of the smoothing of the sea surface or the lack of complete communication with the sea surface. And so fixed SSTs might provide another way to help compare that.
Yeah, we have discussed possibly doing that. No plans per se to do, but yeah, you're right. A fixed SST might be able to help you diagnose some of these questions we're trying to answer in terms of mesoscale eddies or air-sea interaction. But I think you have some fixed SSTs, so maybe now we need to do a mix R for these other time periods like the LGM and or Pliocene.
That's true. Yeah, we could go the other way too. Thanks.
Any other questions? Yes, Ran.
Thanks for the great presentation, Betty. I was curious, so did you guys also look at the differences in heat transport? Because I was wondering that those different climate states, the tropical cyclone state might also contribute to different state in the meridional heat transport.
Yeah, we've looked a little bit at kind of the SST patterns between these different ones, but yeah, basically the diagnostics are a challenge right now in these models because we can't run the old packages anymore, for one thing. Like just, they're going to Python packages now, Esther's grimacing here. So yeah, we haven't looked as closely as we'd like to, which is part of the reason we are going to release them for a little bit until we really can look at them and see. And we'd like to do other time periods, of course. My love is to do the Cretaceous, as and the seaway going up right where we are right now. Tropical cyclones for the dinosaurs.
Okay. Thank you, Betty. We will continue on to our next speaker, Zhang Zhu.
to you, or you're gonna share on that computer?
Yeah.
By setting up, I should say, Sophia's going to look at the atmospheric rivers and the same simulations. So, and I think Ren, you're going to do, and Mary Grace are going to look at mesoscale convective systems.
Background?
How to find
Yeah.
Oh, it's because it's like multiple.
Okay, I will get started. Hello, everyone. I'm Jiang Zhu. This talk is about early Eocene surface temperatures in an unprecedented high-resolution Earth system simulation. And this is in collaboration with Betty Otto-Blisner, Esther Brady, Jess Tierney, Chris Paulson, Ran Feng, Clay Tabor, and Andrew Waters. First, why should we care about the early Eocene, a distant past climate? The reason is that past climates can help inform our future. So this plot shows the CO2 concentration and temperature variation in the past 60 million years and in future projections as well. The idea is that if we can better understand the climate dynamic processes that drive the past climate change, hopefully we can better project the future climate change. And there have been quite a few applications using the early Eocene. For example, here with the major climate forcing CO2 and the temperature response, with this information, you can already directly calculate climate sensitivity. That has been done in the past. And using this forcing temperature response information, we can also assess climate models. And we can also try to combine model simulation and the proxy data to study past changes in the hydroclimate and extreme weather events, including tropical cyclone as well. And let's jump into the early Eocene, which occurred roughly 50 million years ago. And it is a hot house climate. From fossil remains, people have known for several decades now that the early Eocene was very warm, and we have fossil remains from palm trees and crocodiles from polar and mid to high latitudes. That's why people know that it's very warm. And this picture is an artist reconstruction of the early Eocene environment, and you get the idea that it's pretty warm. Of course, we can use quantitative information to reconstruct the surface temperature of sea surface, the left, and the land surface on the right. So basically, we compile the surface temperature records from the deep map compilation. And in comparison, the black line with the shading is the modern temperature. And looking at the tropics, you see that the proxy data suggests that the tropics was roughly on average 10 degrees C warmer than the pre-industrial. And moving towards mid to high latitudes, you see greater warming in the SST. And thus similar features also can be found in the land surface temperature. And those are a lot of information and with a large uncertainty from each individual record. And one way to really summarize the information is to calculate very simple metrics. For example, just calculate the global mean surface temperature for the early Eocene. Here I group the surface temperature records into different latitudinal band and compute the area weighted mean. And based on that simple calculation, early Eocene was 14 degrees C warmer than the pre-industrial climate. And using the tropical SST and the deep ocean temperature, we can estimate the equator to pole temperature gradient. And we estimate that the gradient was reduced by 30% for the early Eocene. And this type of global warming and the reduction in temperature gradient has been challenging for the previous generation of models to simulate. And there's quite some research interest looking into this. So here I first want to summarize available simulations on this topic from CESM family models, CESM2, CESM1, and CESM4, as well as from the DeepMap models. So those are not CESM models. Basically, you can see that overall, CESM1 is a model that best match the early use and records in terms of CO2, which we haven't talked about much. And here the CO2 is from the boron isotope estimation. And then the y-axis is global mean temperature from my simple calculation. So again, you see that CESM1 is the best model to match the temperature and CO2. And also the middle plot shows the temperature gradient. Again, the proxy data suggests 30% reduction, and the models can capture this magnitude of reduction in large-scale temperature gradient as long as you can simulate this amount of global warming. And to really illustrate the use of early use and constraint, we can look at the model climate sensitivity. That's the x-axis here. And you can see that for CESM4 with a low equilibrium climate sensitivity, the model underestimates early use and warming. And for CESM2 with a very high equilibrium climate sensitivity, and the model clearly overestimates the early use and warming from proxy data. So I think this is a powerful way to use the early use and constraint to assess the climate sensitivity in the models. And move on to the regional scale, because before I only showed you the very simple metrics on the large scale temperatures. So here we are comparing the CESM1 simulation, SST, and the land surface temperature against all the proxies in terms of annual mean. And starting from the tropics, or anytime if you see the markers with the edge color of green, it means that the model simulation fall within the proxy suggested range. And looking at the tropics, you can see that the model can simulate the amount of warming seen in proxy, so in good agreement. And over other places, you do see model data discrepancy, especially over the Southwest Pacific, where the proxy suggests the global mean temperature in SST, or the SST, regional SST of 30 degrees C, and the model can only simulate 18 to 12 degrees C. So we have a big model data discrepancy there. And you see similar thing in the land surface temperature over some regions. And another important aspect which has been mentioned today is the above freezing winter temperatures. That's one important element of the equable climate problem. That's this slide is about. But starting from the annual mean, you can see that the model can overall match the temperature in annual mean from the terrestrial records. So now we are looking at the northern hemisphere. Interestingly, if you look at the cold months temperature, so roughly the coldest months of the year, and you see that if we only look at the coastal region, the model is doing an okay job in capturing the above freezing winter temperature. However, if you look at the continental interior, for example, the New Siberian Islands are shown here, and you can see that the model simulate very cold winter, cold months temperature, maybe 10 degrees C below freezing, and which seems inconsistent with the proxy information shown here. And in light of the regional differences in SST and in the seasonal temperature, the question I want to address is, can higher resolution help and further improve the simulation? And I'm going to use the simulation Betty introduced using CESM 1.3 high-res, and we have 10 times finer horizontal resolution than the simulation I have showed you so far. And I'm going to focus on the simulation with 3 times the pre-industrial CO2. And the high resolution was initialized from the low res and run for 60 years. And the simulation is expensive to run, 300 times more expensive in terms of cost per year. And one of the most important motivation for us to perform this high resolution simulation is that with this horizontal resolution, we start to resolve ocean eddies instead of parameterize them. So starting from the lower right corner of the plot, that's the coarse resolution we typically use. And you see that the ocean currents is very sluggish, and we don't have a fine scale feature. And when you increase the horizontal resolution, for example, to the top left, we start to resolve the ocean eddies. Those are the weather events occurred in the ocean. And you see a lot of fine scale structure and much stronger currents. And the scientific question is if we are going to resolve these ocean eddies, what's the impact on the large scale SST? That's what we are going to look at next. So on the left, we have the sea surface temperature in the simulation with high resolution. And in the middle, standard low resolution simulation. On the right, we have the difference. And you can see that in general, we have warming everywhere in the tropics and over mid to high latitudes. But interestingly, the enhanced warming is much greater over the mid to high latitudes. So in a sense that we have reduced the meridional temperature gradient in the high resolution simulation. So that's why I think it shows that high resolution is more equable. And if you look at the cold month temperature, so roughly winter temperature, and the rightmost plot shows the difference between high res and low res. And you can see that not just SST, in the cold months, land surface temperature, the high resolution can give us additional warming of up to 8 degrees C, which is significant. By the way, I forgot to mention that if we look at the Southwest Pacific, the high resolution gives us additional warming of 5 degrees C. So that explains roughly half of the current model data discrepancy there. And then you may wonder, why do we have enhanced warming in this high resolution set of simulation? So again, the leftmost plot is just reproduce the SST warming in the high resolution compared to low res. Then I'm going to use the additional simulation. We call it mixed resolution. In this set of simulation, the atmosphere is still high resolution, but the ocean we use low resolution. And comparing high resolution against mix R, it gives us the row of high resolution ocean. And when you compare the mixed resolution against the low resolution, the difference gives us the row of high resolution atmosphere. And you can see that the enhanced SST warming over mid to high latitudes can be attributed to high resolution ocean, consistent with our understanding that eddy is contributing to this SST warming. And we have SST cooling over lower latitudes. This also consistent with the structure of eddy-induced heat transport change in the meridional direction. And it's also very interesting, you can see that the high resolution atmosphere also gives us additional warming, and it's broadly covers the mid latitude and the tropics. It does not have a lot of spatial structure. And currently, I don't have a good explanation about what's going on in the high resolution atmosphere. Okay, next, let's move on to look at the cold month temperature. So again, the leftmost is high resolution minus low resolution. And in the middle, we have row contribution from a high resolution ocean. And you can see that the SST warming in high resolution can help you to warm the coastal region. So I think that makes physical sense. And if you look at the rightmost plots, so that's the additional warming over cold months can be attributed to high resolution atmosphere. So you see a broader warming over the continental interior. So this may be related to convection clouds, etc. Okay, that's my presentation. I want to quickly summarize. And I have showed you that low resolution simulation CESM1 is a model that best match the proxy records in terms of global mean temperature and temperature gradient. However, we still have large model data discrepancy at a regional scale. And I showed you also that when we use much higher resolution same model CESM1, and we see that enhanced warming over mid to high latitudes, we have reduced temperature gradient, and we have much warmer cold months temperature as well. And part of this warming can be attributed to high resolution ocean, likely through resolving ocean eddy. Part can be attributed to atmospheric processes, likely related to convection and clouds. And one final comment I want to make is that when this new high resolution capability become more and more available to people, we really need better regional seasonal reconstruction from proxy, and preferably using multiple records with a precise location reconstruction, which will be important to leverage the high resolution capability from the models. And then with that, I will stop and thank you for your attention.
Thank you. Looks like we have a question from Mohammed.
Hi, thank you so much for the great presentation. So I have 3 questions for the ICESM 1.3 high resolution. So first question is like, what were the time duration of the whole simulation period? And the second question is, what is the highest temporal resolution? And the third question is, does it have delta 18, delta D, and DXS available for the simulation? Thank you.
Yeah, so thanks for the questions. So in this talk, I showed the simulation of the early EOSM, and everything follows the deep map protocol. And for the high resolution, we do have isotope capability, so including water isotopes and including delta 18O, delta D. And about the horizontal resolution, as you can see here, we are using roughly a 1/4 degree atmosphere and a 10th degree ocean. And Sophia showed in her presentation earlier, you can go finer when you use a regional configuration.
I was actually asking about the temporal resolution. Like, was it like 6 hourly or daily or?
Yeah. So, like Betty mentioned, this set of simulation is very expensive to run, and that's the reason we saved a lot of model output at multiple frequency. We include, for some fields, we even include 3 hourly output. So daily, we have a lot of variables at that frequency as well.
Okay, so it's like, just to clarify the question about the duration. So for the modern time, like not the past climate, but for the modern time, like what was the duration like? Was it like from 1850 to 2015, for example? Or
Yeah, we didn't do that simulation, but for the pre-industrial, based on the paper, they have run the simulation for more than 500 years. And for the RCP, I think they started from 1950, but I might be wrong.
Okay, makes sense. Thank you so much.
Is there any sea ice in these simulations, and does that change at all with the resolutions?
There's no sea ice at this CO2 level.
Okay.
So roughly when your global mean temperature is above 22, 23, that's where in CESM1, you no longer have sea ice cover.
Okay.
Lots of sea ice in the LGM.
Yeah.
Yeah.
I have a question, which is, have you had time to recreate that, proxy model output comparison with the red and green outlines for the proxies with your high resolution run? And if you did, does kind of resolution alone resolve a lot of those discrepancies, or are there additional things we should consider?
Yeah, thanks for the question. Roughly about this plot. Right?
Yeah.
So over the Southwest Pacific, again, here we are looking at the simulation with 6 time pre-industrial. But assuming we can add the anomaly from the high resolution over this region, which is roughly 5 degrees C. So we explain close to 50% of the model data discrepancy over the Southwest Pacific. And for other regions, and I don't know.
Okay.
Thanks for the question.
Yes. Ren.
Oh yeah. John, I was wondering, so there's a lot of at least data model comparison, especially for the coastal records, always end up with the conclusion that they don't match because the simulations aren't resolving the coastal upwelling correctly. So I was just wondering, the high-res simulations, do you see differences in simulated sea surface temperature, especially along the coast?
Mm-hmm. Yeah, thanks for the question, Ryan. The rightmost plots, if we focus on the coastal region, you see that maybe the high resolution is warmer by 1 degree C roughly. And I think maybe if we run the simulation longer, we may see a bigger signal, and it was exploring because the coastal upwelling is not like only wind-driven and wind-driven upwelling processes. There are geostrophic components, there are ocean basin adjustments. So again, to answer your question, we have some small signal, but maybe if we run longer, we might be able to see a bigger impact.
Okay, great, thank you.
Is there a seasonal component that is kind of, it's being smoothed out a bit by them showing mean annual?
Yeah,
change?
okay, could be a good
partially.
point, yeah.
Also, maybe not a question for you, but maybe Anthony knows. I know there's a lot of new analysis on the TEX 86 and the fact that how you calibrate it just to temperature when there's biology and salinity. You were showing TEX 86 for the your runs.
Yeah,
They always seem to be a lot warmer than some of the other records.
yeah, I don't know. I'm not a text 86 specialist. But what I've seen for the Cretaceous, that those text 86 record like so there's very high temperature that are probably unlikely at some location. Then I guess like Jess or like people from this community might be better able to answer this question.
Okay, we don't have any other questions. Let's get to our last presentation for the Paleoclimate Working Group meeting today. And again, Zhangzu is going to go over some CESM 3 updates for us.
Okay, thank you again, everyone, for sticking around. I will spend a couple minutes, give you an update about CESM 3 timeline, if you are interested in this. And hopefully we have some time for wrap-up discussion at the end. So here is a timeline, a proposed timeline for CESM 3. And we are here at the beginning, roughly February 2024. The next big event is the CESM 3 science freeze. So roughly means that the developers will determine which major model parameterization will go into the model. And that is targeted for summer this year. And after that, we will have like tuning and further development of simulations. Then the final release of CESM 3 code and a set of some evaluation simulations will be is targeted for early 2025, so early next year. And after the release of the code, you can see there are some planned interesting work on machine learning and high resolution application as well. And then there's active involvement and contribution from the Paleoclimate Working Group. And this time we will use the last glacial maximum simulation as an out-of-sample test to provide early feedback to model development. And this is motivated by our past work on the paleoclimate calibrated CESM2. And we identified issues in the standard CESM tool, and since then those have been dealt with. And also we are working on investigating CESM tool simulation of the early Eocene. We run into the problem that the temperature is not converging for under warm conditions, leading to model crash. And please check out my talk at the Atmosphere Model Working Group meeting if you are interested in this topic. And the talks are available on YouTube, CGG. And here I try to list a few notable things from the atmosphere groups. This is by no means to be inclusive. And again, please go to their recordings of the meeting if you want to learn more. And one major difference from the new atmosphere model CAM7 is that we will have a new spectral element dynamic core. And panel A shows the grid. And this is a modern dicore, meaning that has better scaling. And when you use higher CPU number, in general, you get better model throughput. So that's a nice feature for high resolution application. And the panel B shows a grid. Sophia already showed that. So this spectral element dicore has very nice support for variable resolution simulation. And this could be beneficial for some type of paleo research. And you can see this is unstructured grid, meaning that we need to adjust our workflow for analysis and data visualization. And CAM7 will have much more vertical levels than CAM6, so 93. And there's a low top configuration of 58 level that is used for parameterization development. And CAM7 will likely use a new radiation scheme, RTE-RTMGP. And this is more accurate, has a wider lookup table. Please check out talks by Brian Medeiros and myself if you are interested in learning more about this new radiation and what's the potential implication for your research. And in CESM3, we will use a new dust scheme. Check out this talk if you want to know more. And roughly, the dust mobilization will be treated, will have this partition will be treated differently by the surface roughness, and the subgrid turbulence will be accounted for, which should be more realistic. And the erodibility map has been moved from the atmosphere to the land model. And from CESM3, we will have a new ocean model. So that's very different from the past decades. So this is a table from the talk by Gustavo. And please watch the recording if you are interested. And basically, this table tries to list the major differences between the old ocean model POP2 and the new ocean model MOM6. And the elements that might be relevant to paleo include the horizontal grid. So as for now, the southern limit of the grid is around 81 degrees south. And we are working with the land model working group people and talking to oceanographers. We hope that
Sorry.
we hope that we could extend the grid further south to benefit paleo simulation of past warm climates. And another nice feature about the new ocean model MOM6 is that it's no longer volume conserved. It has variable mass, meaning that we can use more realistic natural surface freshwater flux. So that's different from POP, in which we use the virtual salinity flux. So this is a nice feature, means that likely we won't run into negative salinity problem in our high CO2 warm climate simulation. So this is nice. And MOM6 offers multiple choices of vertical coordinates, and we are still communicating with oceanographers about what potential implication for paleoclimate. And we need to work with them later on whether we want to modify the mixing for the deep time application. And if you want to learn more about MOM6, there's also recordings from the past webinars. I find those very helpful. And some other stuff from the other working groups. So again, notable talks, including one by Gunter Legge, Bill Lipscomb, and Dave Bailey. And the land ice model working groups, they are working on the Antarctic ice sheet in CSM3 and the coupling with the ocean model. And from CSM3, they will add some support to paleo ice sheets as well. So this can enable more paleo work on the ice sheet and climate interaction. And Bill has a talk on the mountain glacier simulation using CSM2, I think, which is also interesting. And Dave showed a nice notebook on sea ice diagnostics, and check it out if you want to use that. And I would encourage people to participate in the other working group meetings. And there's one starting from tomorrow, and there's more to come. And another thing I want to mention is that from CSM3, we will have this new coupling infrastructure, NUOPSI and CMAPS. I don't know a lot about this new infrastructure, but one nice feature is that we don't need to generate mapping files offline now. So this really simplifies our workflow. So stay tuned on that. So finally, some technical updates about derecho, GLADE diagnostics, and CSM versions. So based on all our exploration, the good news is that derecho is in general faster and cheaper than Shanyan. And just a reminder, please submit a support ticket if you forgot to get data from GLADE P Power Working Group. And there are a few initiatives on model diagnostics and data visualization, including this new diagnostic package, and see the talks at the software engineer working group meeting in a few days. And I also find the Earth System Data Science Initiative, they have this website, very helpful. For example, you can find their blogs documenting how to visualize the model output from CAM-SE. So check it out if you are interested. Finally, about the model version, CSM 2.1.5 is a supported and recommended version. It runs on derecho. And if you want to do some paleo work on ice age or very warm climate, you can use the paleo calibrated configuration as long as you don't use very high CO2. So CO2 lower than 6 times pre-industrial level. And Betty already mentioned the high resolution version code of CSM 1.3, and it's supported, it runs on derecho. And Chang et al. Has documented the high resolution and the standard resolution configurations. The code is available on GitHub. And we have added water isotopes into this high resolution version of CSM 1.3. And we are still evaluating the results. And we plan to release the code later, hopefully this summer. That's all I want to say, and thank you.
I was reading the email from Sizzle this morning. On Wednesday, that's in 2 days, Blade P is going to be unmounted. So if you're going to do anything, it's got to be today or tomorrow.
Yeah, thanks.
It's gone.
Any questions? Yes.
Hey, John. I was wondering, so is there any help for like deep time people who develop those simulations to maybe try out some of the tools because it will be very difficult to just like have this model released, and then there might be some README files there, and then if somebody tried to use those tools in the code base to develop something, this could be very difficult. So I was just wondering, is there any chance, or is there any like tools that are developed somewhere that modeler folks can start trying it out?
Thanks, Ryan. So we just started working on CSM3 LGM simulation. I imagine we will use some helpful programs or tools, and maybe other people are interested, and we can certainly share those, at least our steps, when it becomes available.
Yeah, that would be great. I mean, we would be interested in trying out some of the tools, maybe not run the code, but to actually develop some of the boundary conditions along the way.
Yeah, just to clarify, I think using CSM3, we don't need to generate mapping files, but I need to confirm we still need to develop the atmosphere topography, landscape distribution, domain, etc. So
yeah, and the difficult thing is actually the land surface data set, if it's very different, if the land model has changed. And also bathymetry is always very difficult as well.
Yeah.
I don't know if mom would be easier than pop.
I don't know.
I should note,
fingers crossed.
CSM3, or the ocean model, that uses a tripolar grid. So poles in the northern hemisphere and one in the southern. So that can be a challenge, though we've already had to do that in CSM 1.3, so we have some experience with that.
Yeah.
Yeah, it's just, I was just gonna say in the past also, like, there are various great cells needs to be fixed so you don't have strange ocean current that are restricted. So yeah.
I'm looking at the chat. Thank you, Dave. And Dave had a comment in the chat saying that new mesh files must be created for a new domain. So again, there will be a lot of work to develop new set of paleoclimate simulation. Hopefully we will, and we will share our steps with people when they become available.
Yeah, thanks. That would be great.
Will isotopes be available in CSM3?
No.
We have a proposal in to get them in, but we will see. As you know, we didn't get them in CSM True, but it was mainly the land model that held us up. So we'll see. I don't know how hard it's going to be in MOM.
They're already in the sea ice model.
Yes,
Dave has
sea ice
mentioned
and the land
in the
ice,
chat.
but I'm not sure, and they're kind of in
Ice.
the atmosphere model, but I
6.
don't know about the land or the ocean, where we'd like them.
Definitely not in the ocean. That's what Dave just said.
Okay.
Thanks, Dave. Is it going to be hard, Dave? He didn't say.
I'm not sure, actually. I mean, MOM has tracer modules and stuff like that, and so, but it's just a resource issue. Who's going to be the person to do it?
I think the GIS model used MOM and an older version of MOM as their base, their ocean code, and that has isotopes in it. So it's possible that that can kind of translate into MOM 6. I don't know. Yeah.
Yeah, Ren?
Yeah, I have another question. So, John, you mentioned the spectral element and the cube sphere grid. So I was wondering, so is CESM3 going to complete ditch finite volume?
That you can check out the talk by Peter Lauritsen. I think at the end of the Atmosphere Working Group meeting, he gave a presentation about his view on the future dicots in CSM. And currently, CSM supports multiple dicot, including the spectral transform dicot. That one they plan to retire soon. And for finite volume, it may stay longer, but we need to go back to Peter's talk to be sure.
Okay, got you. Thank you.
There is kind of an equivalence, though, in the spectral elements. So I didn't say that in my talk, but the when we said we used an NE30, no, NE120, they should take that back, NE120, so it was a spectral element core for our high res, and our low res is an NE30, which is kind of the 1 degree. And then you could actually run NE16, which is a more like a 2 degrees. So there is kind of different spectral element resolutions that kind of parallel having done lower finite volume.
Okay.
One small question. This isn't exactly CSM3, but you mentioned the last spatial maximum simulations. Are there any updates to like the boundary conditions and things like that for like the LGM simulations, or are those going to be kind of just like using the same of what was in, I guess, PMIP 4 maybe? Just curious if there's any movement on any changes to those.
I don't know there's new efforts on the boundary condition. At least the paper documenting the experimental setup from PMIP 5 and not being put together. So I think that we are dealing with a new ocean model this time. This is really something new for us. So we can start doing this step by step, meaning that we can use the older configuration. So we have a comparison with older runs at the same time. And then we can add new boundary condition if PMIP 5 is going to provide us about guidance about this, how to set up the new boundary condition.
Yeah, I don't think PMIP 5 has gotten that far.
Yeah.
But I do know, and you could comment, that DeepMIP and MyoMIP are both working on new protocols and new boundary conditions. Well, MyoMIP is new. DeepMIP is. PleioMIP does have their paper out, and basically they're not changing anything.
Okay.
Speak of, but they've added some experiments. So they have an early Pliocene where they open up the Central American Seaway, and then, but in general, they're trying to keep it easy for modelers to adapt it. So, but it was in, why can't I think of it? I'm an author on it. I'll think about it. It's already published. Look up Alan Haywood and find it in PleioMIP 3.
Okay, thanks.
There are quite a few interesting discussion in the chat. I want to go to Dave first. I think he referred to the GACE model. Please correct me if I'm wrong. The GACE uses MPass ocean and sea ice. The atmosphere component is similar.
No, it was Rich who asked about E3SM.
Okay, I see.
Whether that was there could be some synergy there.
Okay, I see.
Yeah.
Okay, so that's basically the question from Clay. So could there be any synergy between E3SM effort to add water isotopes any overlap with the model components. So Dave answered the question that at least the atmosphere is similar. And luckily Rich is here. Rich, do you have any comments?
Rich, yeah. You might be muted, Rich. Still here? He's still there. He should be there. I mean, it'd be interesting, Rich, to know what you're doing with the land model in E3SM, because that's been kind of a whole challenge.
E3SM.
Oh, will you stop presenting the screen?
Oh, okay.
Here we go.
Okay.
It's bigger. Nice.
I see.
We don't
Rich
see
is still on.
Rich.
Well, Rich said, I was wondering that too. We can discuss more. I saw Zhang mention microphysics and CAM7 are changing. Do we know to what land is similar to?
I think I'm back now. Can you hear me now?
Oh, great.
Yeah, sorry, mic issue. Yeah, I think the land and the atmosphere are still similar enough. Of course, we lost isotope tracers in CLM5. And where the land model branched off for E3SM, it was at 4.5, which also didn't have isotopes. And so that capability will need to be reconstructed. But I think that ELM2 and CLM5 and future versions should be a little bit more similar. And so there probably are some opportunities to work together on that. The atmosphere model is pretty similar, I guess, except for the microphysics now, and the microphysics is changing in E3SM to something a bit different. But I think that scheme actually had water isotopes in it, possibly in WRF. And so there may be some opportunities to pull that over too.
Nice.
Just to follow up, to answer your question about microphysics in CAM7, CAM7 will use PUMAS. That's basically an updated version of MG3. And it will be different from T3.
Yep.
Okay. Does anyone have any last questions or comments or reflections on the day? No? Okay. If not, thank you everyone so much for attending the Paleoclimate Working Group meeting today. And let's thank all of our speakers again.